Okay, let me give you a moment to copy this example down, and then we'll discuss the solution to this example from section 6.2, volumes. Okay, so in this section now, in this problem, what are we being asked to do here? Well, all right, let me make this a little bit bigger for me. And you know there's a zoom thing on the left there. You can magnify the example. So we want to find the volume of the solid obtained by rotating the region enclosed by the curves y equals x and y equals x squared about the x-axis. What is the first thing that we are going to have to do here for this problem? Well, all right, Yonatan, we need to find points of intersection. And Victoria and Shalom are correct. Also, we need to graph the problem. So we're going to graph, and we can do this on Desmos, right? We can graph y equals x. We can graph that line. We can graph this parabola y equals x squared. And then we're going to rotate that region about the x-axis. Okay, so let's see how this works. Okay, so here, in my solution, here's a picture. Now, you don't need to worry about the terminology washers. I'm not worried about the terminology. Okay. Okay, so let's see what we have here. Well, here's the line. Here's the line y equals x. And here's the parabola y equals x squared. And this here is our region. And we're rotating that region about the x-axis. Okay. So it's like, okay, so then if we did that, then, you know, we would generate a volume that would basically, well, what would this volume look like? So it's not like a closed volume. It's not the closed volume, but we can think of this as, well, we could think of it as taking the volume of a, hold on, let me put it in red. We could think of it, the volume we want, as taking the volume of a cone. Okay, we're taking the volume of a cone. Okay, let's try to draw that a little bit here. Taking the volume of a cone and subtracting out this inside volume. What's that inside volume resemble? What kind of chocolate? Reminds me of a chocolate.
Kisses.
Hershey's Kisses. That's right, Daniel. That's right, Victoria. That's right, IB. So think if you had a cone, and you were to cut out from the center of the cone a Hershey's Kiss. The volume of the cone left would be that what we're interested in. And the best way to get that volume is to say, well, let me find an outer volume minus an inner volume. Okay, so if we were to find the volume of the cone and subtract the volume of the Hershey's Kiss, okay, which I pictorially, have laid out here, just a little picture, that'll get us the volume we're interested in. So this problem requires us to find two volumes: the volume of the cone, which is the outer volume, and the volume of the Hershey's Kiss, which is the inner volume. Well, now, if you remember, volume, okay, we talked about this last Wednesday. We derived, actually the book derives, that the volume is equal to the integral from A to B of the area AX, the cross-sectional area AX. So we like to create volumes by rotating regions about some kind of axis, because it allows us to easily find the cross-sectional area, because the cross-sectional area would be a circle. Okay, so in other words, if we look here, if we were to just take, and let me turn off my internet here. I don't want any distractions here, so let me turn that off. Okay. Yeah, if we look at this X value here, and we were to look at this cross-sectional area, what's the cross-sectional area look like?
A circle?
That's right. Let me actually, that's right, Clea. Let me put it here, okay, Mike. And let me draw cross-sectional area here. So definitely a circle, right? Definitely a circle. So, like for instance, if we look at the inner volume, okay, which is the Hershey's Kiss. So how would we? And again, let's keep in mind, volume of a solid is equal to the integral from A to B of the cross-sectional area dx. So what we need to find is an expression for the cross-sectional area. Well, the cross-sectional area, you can clearly see it's a circle, right? It is a circle. And the area of a circle is, as you know, pi r squared. So here, maybe I'll even put it in blue. Here, here's the radius. The radius goes from this point to this point. Well, what would the radius equal? Well, for this inner volume, you know, again, pi r squared, the radius is x squared. Because you're going, you know, what is that distance equal to? That distance is equal to x squared, which is the top y value, minus 0, which is the bottom y value. And that gives you x squared. So the inner volume, and the limits go from 0 to 1, not hard to see that those are the intersection points between that line and the plane, or line and the parabola. So the volume then is going to be, for the Hershey's Kiss, is the integral from 0 to 1 of pi times x squared squared dx. That's the inner volume. Are there any questions on that?
Professor, so when finding the volume, we use the formula of the volume of the circle?
Well, the volume for a solid is equal to the integral from a to b of a of x dx.
Yeah.
A of x is your this is your cross-sectional area. Cross-sectional area. So what you're doing is you're taking, I mean, what would you do to find the volume of the Hershey's Kiss? You would take cross sections of the Hershey's Kiss. Those would be disks with cross-sectional area A of x. But the disks are going to have different cross-sectional areas depending on where your x value is, where you're cutting the Hershey's Kiss, where you're making that cross-sectional cut. The radius is the difference of y values. Well, the y value for the parabola is just x squared, y equals x squared. The y value for the x-axis is just y equals 0, hence x squared minus 0. And so this gets you your inner volume. Does this, Clea, does that help you feel comfortable, or?
I guess.
Okay.
Professor, I have a question too.
Yeah, Shalom.
So can you explain to me how we found the cross-sectional area, and then after that, can you explain, like, in scenarios why we would have a different cross-sectional area? Because to me right now, it just looks like it's always a circle.
I'll tell you what. Let me bring up the ebook for a moment.
All right,
we'll come back to this. Let me come back to this. Let me bring up the ebook. One moment. Okay, we'll come back to this. So what we're really doing here is we're using disks. We're using the disk method to approximate the volume. So in example 2 from section 6.2, we had talked about this last Wednesday, but I know that was a little while ago. So Here they want you to find the volume of the solid obtained in example 2 by rotating about the x-axis the region under the curve y equals square root of x from 0 to 1. Okay, so what we do is, here's figure 6. Okay, and there is the region bounded below by the x-axis, above by the square root of x, and on the right, well, the x limits are from 0 to 1. If you rotate that region about the x-axis, you see there you generate that bowl in the figure 6, the second picture. Well, the bowl, you can like take cross-sectional slabs of the bowl, and every cross-sectional slab will be a disc. There's a purple disc right there. So the cross-sectional area, though, of every disc is a circle, and the circle would have an area of pi r squared. Well, what's r squared? Well, look at figure 6 there. Look a little bit and look at the first picture. Do you see the radius equals square root of x? That would be your radius. Are there any questions on that?
No, that made it much more clear. Thank you.
Okay, good. And then of course the volume would just equal the integral from 0 to 1 of pi times the square root of x squared, which is pi times x dx. And incidentally, we can do this if we wanted to rotate a solid about the y-axis, we could do that too. Okay, so in example 3, they want you to rotate the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. Okay, so for that, we just we go to figure 7, and there is okay. That one question I'll get back to on break. IB, I saw your question there. So y equals x cubed is there in figure 7, and x equals 0 and y equals 8. So that's the region. You rotate it about the y-axis, and you see you can approximate that in the second picture. You can approximate that volume using horizontal discs with delta y as the width, and then the radius is going to be that distance from the y equals x cubed to the axis of rotation, which is the y-axis. But it's a difference in x values. So y equals x cubed, you're going to write as x equals the cube root of y, and subtract x equals 0 from x equals cube root of y. And so that will get you then, your, I want to say this the right way. Hold on here. One moment. Let me just see if they, yeah, this is what I'm looking for actually. Yeah, so the radius is just the cube root of y. That's the horizontal radius. And if you square that, you'll get pi times y to the 2/3 power, because the cube root of y is y to the 3rd. And if you square that, you multiply the exponents, that gets you y to the 2/3 power. And so for this problem, the cross-sectional, well, the cross-sectional area is just pi times y to the 2/3 power. And then that allows you to get the volume for this situation. So these problems here in these examples, and again, those are examples, let me make sure I have them phrased correctly. Those are examples 2 and 3 in section 6.2. There you're finding a volume of a solid that's completely includes everything inside, inside the surface. But now with the example we're looking at, okay, we're finding the volume of, well, the volume that we're finding here, okay, and I can write it out. What I mean is I can shade it again. The volume that we're finding is the volume found by taking this region and rotating it about the x-axis. Okay, so the volume is not completely enclosed. So you have to extract out the volume of this Hershey's Kiss here. You have to find that volume and subtract it from the volume of the outer cone. Well, the cross-sectional area of this Hershey's Kiss is going to be a circle. It's going to be a circle. And it's going to be a circle that has this radius here. Well, what is that radius there? That radius is this distance, which is a distance of y values, namely y equals 0 and y equals x squared. Well, that distance, if you take x squared, which is the higher y value, and subtract y equals 0, that gets you x squared. And so therefore, the radius of the Hershey's Kiss is x squared, just x squared, and you'll square that. So this here is pi times r squared. See, that's why this works. And for the outer volume, of course, is going to be the cone. The cone, right? So the cone is your outer volume. Okay, and the cross-sectional area for that would also be a circle. Right? It would be a circle. But what's its radius? What's its radius? Well, this is the distance, this is the radius. So that radius goes from y equals x minus y equals 0. That's your radius, which is x. It's no different than like if you have a vertical number line, and if you have 3 and 7, what's the distance? Higher y value minus lower y value, 7 minus 3. Same kind of thing. And so for the outer volume, the radius is x. And you're doing pi squared. So the outer volume minus the inner volume, well, you're going to get, I mean, if we wanted to write this integral a little more in a little nicer way, we could, I mean, this is beautiful what's here, but we could write this as 0, the integral from 0 to 1 of pi times x squared minus x to the 4th dx. That would be fine. Okay, and then that integral, if you factor out a pi, you'll get the integral from 0 to 1 of pi times x squared minus x to the 4th dx. And it's an easy antiderivative to do, right? It's an easy antiderivative to do. It's just equal to pi times x cubed over 3 minus x to the 5th over 5 from 0 to 1. And if you plug the 1 and the 0 in, you're going to get a third minus a fifth times pi, which is 2/15 pi. That's the volume. That's the volume of this interesting solid that we get. It's like a hat, you know. You ever see those? I guess I don't know if it's Asia where the folks are working in the rice paddies and they're wearing those hats. Kind of reminds me of the volume of one of those hats that we're looking for. But we get 2 pi over 15, and that's what WebAssign's going to want. Okay, it's not going to want a decimal approximation. It wants the exact answer. And that'll be true on your exam too, your second exam. Yes, Clea, question?
Yeah, so like I'm having kind of difficulty with like the radius. It's like why in the outer one is x and in the smaller one is x squared?
Well, I'll show you here. I'll show you. Before I show that, are there any questions? So I left out some work here, okay? I mean, what I mean is in the solution, well, I did work here, right? But I know you could do this integral. I know you'd have no problem finding the volume of the cone and the Hershey's Kiss and subtracting those volumes. So Clea, you are correct that the radius is key, right? The radius is key. You can't get these volumes without understanding the radius. So I mean, isn't this the radius here for the Hershey's Kiss? See what I'm drawing there?
Yeah.
That's the radius, right?
Yep.
So what's the value of the radius? It's this distance here from these 2 points, these 2 y values. Well, the top y value is x squared. The bottom y value is, well, the x-axis, which is y equals 0. So the inner radius is x squared. X squared minus 0 is x squared. So far, so good?
Yeah.
Okay. Now we have the outer radius. That goes from the axis of rotation, which is the x-axis, up to the line y equals x. That's what it goes to. And so, you know, if you take this distance here, it would just be, you know, y equals x minus y equals 0. And that gets you an outer radius of x.
Oh, now I get it. Yeah.
Okay, good, good, good. All right. Are there any other good questions? Susanna, yes.
I'm a little confused why wouldn't we use, I see the area of a cone is pi r squared and then the height over
Well,
3.
I mean, indeed, there is a formula for the volume of a cone, but the thing is, you're going to be dealing with a lot of volumes where, you know, you can't get the formula doesn't exist for, and so it's just good to get used to doing it this way. That way, you don't have to remember the volume of a cone. But I mean, yeah. You'll see why we're doing it this way, you know, with our next example. I'm actually glad you asked that question. The next example, I think, will be very, very informative. So hold that thought, all right, Susanna?
Okay, thank you.
Okay. So Shalom is actually asking a good question. You're welcome. Shalom's actually asking a good question here. Could you rotate a region about an axis that's not the x-axis or the y-axis? And the answer is yes. That's what we're doing in example 2. So let me give you a moment, or I shouldn't say example 2, but this example. So let me give you a moment to copy the example down, and then we'll go over it. Okay, so let's take a look at what we have here now. Here, we want to find an expression for the volume of the solid obtained by rotating the region enclosed by the curves y equals x squared, which is a parabola, and then another parabola, sideways parabola, x equals y squared. So we want to find the volume of the solid obtained by rotating the region enclosed by these curves about the line x equals -1. X equals -1. So now x equals -1 is this a vertical line or a horizontal line? X equals -1.
Vertical.
That's right, Clea. That's right, Jonathan. That's a vertical line. A vertical line. So, I mean, what do we need to definitely do? I mean, you know, so now we're going to actually find the volume then, you know, but before we try to even find the volume, you know, with integration, what do we need to do first for this problem?
Build a graph.
Build a graph. That's right. And Mohammed's right. We need to find points of intersection. Well, the points of intersection you could find that it's not too hard. You know, the y equals, y equals x squared and x equals y squared. So how would you find the points of intersection? Well, you could take the x equals y squared and substitute it in the first equation. And if you did that, you'd have y equals y squared squared, or y equals y to the fourth, or y to the fourth equals y, or y to the fourth minus y equals 0. And then you can factor y out and you'll get y times y cubed minus 1 equals 0. Okay, and it turns out that y equals 0 or y equals 1 is going to be the intersection points. But how many of you would graph y equals x squared and x equals y squared on Desmos and just look and see where the intersection points are? How many were doing that with the homework you just did? Okay, Clay is a yes on that. Mohammed, yeah. All right. So, you know, we want to. Yes, I think that was Avery or Daniel who commented yes. So, I mean, it's not too hard to see that the intersection points here are going to be the origin and 1, 1. So let's go ahead here to our solution. Oh my goodness, we have an example here. We have a solution. We have a figure to copy. So what I'm doing, and I'm going to let you copy the figure. I'm going to give you a moment to do that. But this is our region here. Okay, bounded by the parabola y equals x squared. Bounded below, and then bounded above by the parabola x equals y squared. Okay, and we're rotating that region about the vertical axis. Hold that thought. I should say the vertical line, x equals -1. And if we rotate that about that vertical line, this will be the mirror image. Hold on, I gotta do that. This will be the mirror image of that region. And we're interested then, you know, in finding the volume of this, and I'm sorry, I'm doing it with my mouse here, but we're interested in finding that volume. So this is going to be another problem where we do inner minus outer volume. Mohammed, did you have a question? Was that you?
Yeah, I was gonna ask for the bottom bound equation, would you be able to just square wait, sorry, one second. Yeah, would you be able to just square both sides and solve in respect to y instead of solving for x?
Let's see. You mean for when we found the intersection points?
Yeah, so like when you did like, so you have x equals y squared and then y equals x squared, wouldn't you just be able to square both sides and solve it that way as well for the y equals x squared?
Well, you have to somehow put the one equation in the other equation. You have to, because at the points of intersection, both the equations are true at once. So you have y equals x squared, but then you also have x equals y squared. And at the points of intersection, both equations are true. So that's why the x equal, or the y equals x squared, I'm going to take for this x here, I'm going to substitute in what x is on the second equation. You see, it's like I'm utilizing the information of both equations at the same time, because, which I can do, because at the points of intersection, both equations are true. What did you, I mean, what were you thinking of doing? If you want, you can use the pen.
Oh no, I was just saying, like instead of having y equals x squared and then x equals y squared, wouldn't I just be able to do like y squared equals x to the fourth, or like, is that not?
Yeah, you could also, you could do that. You could do it this way. Yeah, I see what you're saying. What you're saying is this. Okay. What Mohammed's saying is we have y equals x squared and x equals y squared. So why not take the y equals x squared and substitute it in for y on the second equation? And if you did, you'd have x equals x squared to the fourth power. So x would equal x to the fourth power. So x to the fourth minus x equals 0. And then you factor and you get x times x cubed minus 1 equals 0. And then solutions would be x equals 0 and x equals 1. And that would imply then that, you substitute those back in your equations. That would mean then that y equals 0 and y equals 1 as well. So in other words, what I'm trying to say is when x is 0, y is 0. And when x is 1, y is 1. So yes, Mohammed, you could do that. And that would get you the two intersection points also.
Okay,
Good question.
thank you.
Let's see, Mark is asking, how about all equations in terms of x? Yeah, you could do that, Mark. You could write y equals the square root of x. Yeah, you could do that because you're limiting yourself. I mean, you could, what Mark's saying is this. What Mark's saying is this. He's saying, look, y equals x squared, or no, the second equation, x equals y squared, can be written as y equals root x. But it's really y equals plus or minus root x. But since you're staying above the x-axis, you could say y equals root x, and then you could substitute y equals root x in the second equation. That would get you x equals positive square root of x squared. x equals x squared. So x squared minus x equals 0. And so x times x minus 1 equals 0. So x is 0 and x is 1. And sure, Mark, that's fine. Yep, absolutely, absolutely fine.
I have a question.
Sure, Shalom.
In the equations at the bottom, it says it has +1. Is that because we created a new center?
That's right. And let's talk about that. Let's talk about that. One moment. One moment. All right, I'm going to go ahead. I mean, this is all in the recording, what I just put in here. So, all right. So we need here to find the volume. Hold on here. We need to find the volume found by rotating that region about the line, the vertical line, x equals -1. So if you think about it, the volume that you're looking for would be the volume taking, well, I can't get it. I got to do it this way. If you take the outer volume here and subtract out the inner volume, that would get you the volume you want. So the outer volume is this volume, right? It's this big dish looking thing. So what's the radius for that big dish? Well, all right, I need the outer radius. So here is the left part of the radius. Here's the right part of the radius. So that's the difference though in x values. That's a horizontal radius. So it's no different if I had, an x-axis and I said, hey, tell me the difference between 3 and 7. You would say 7 minus 3, right? Well, same thing here. I'm going to take the bigger value and subtract the smaller value. Well, the bigger value is on the parabola y equals x squared, but then that means x equals positive root y. So I'm going to take positive root y, that x value, and subtract the x value of -1. And that's going to get me a radius then for the outer volume, of square root of y plus 1. Okay, that just comes from taking root y and subtracting -1.
Professor?
Yeah, Clea.
So I get the radius, but like, could we use like the x's instead of the y's here, or?
No, you have to use, in this case, you have to integrate with respect to y. Because, good question, because if you think about it, like discs, okay, discs, like there's a disc. I mean, it's just think of it like a disc, and you're looking at the front of the disc. The width is delta y. So it's like areas. Remember with areas, where if you had delta y, your integral would be with respect to y. Well, if I'm going to inscribe a bunch of discs to fill this volume up, the discs would have width delta y instead of delta x. And so this one here, you have to do it with respect to y. Good question. Now the inner radius. Okay, so for the inner volume, which looks kind of like a vase, I don't know, a dish in that form. Okay, I mean the inner volume, right, would be, if I can shade that in red. This is the inner volume. And so the radius is going to go from the x equals -1 to to x equals y squared. And therefore, your radius is the difference of y squared minus -1. It's the difference in those x values. And so that's going to get you then y squared plus 1. So there you have y squared minus -1. So, you know, you have pi r squared as your cross-sectional area. And this whole thing, this would be how you compute the volume. So your integration is not your #1 concern here, not yet. You got to find a good expression for finding the volume. And it's going to be the difference of those two integrals. Are there any questions on that? Okay, well, so naturally, root y plus 1 squared is root y plus 1 times root y plus 1. I'm going to have to FOIL that, right? And then the other part, the y squared plus 1 squared, let me just get myself a little space here. Hold on, it's easier to erase with the mouse for some reason. So y squared plus 1 squared, of course, for that, that's going to be just y squared plus 1 times y squared plus 1. Okay, and so if we go to the next page, I expand those out, as you see here. Let's see, Jonathan asks, is the positive one from the x-axis equaling -1? Oh, no, where that comes from is you're integrating with respect to y. So like what these volumes, the smallest y value is 0. The largest y value is 1. So you go from y equals 0 to y equals 1. That's how we're getting that. All right, Jonathan? No. The radius. So this here, this is your inner radius, and this here is your outer radius. So y squared minus a -1 is your inner radius, and root y minus -1 is your outer radius. Well, so your inner radius then would be y squared plus 1. Your outer radius is square root of y plus 1. The plot. This is a radius. This is a radius. This here, y squared plus 1 is a radius, and you get the radius by from your graph. Okay. And when you work this out, okay, so I mean, there's some work to do here, but I work it out a little bit for you here. It's really just calculus 1. These antiderivatives you learned in calculus 1. So let me give you a moment to copy. Please let me know if you have any questions.
So these two equations, they aren't like, I'm talking about y plus 2y to the half plus 1 and y fourth plus 2y squared plus 1.
Okay.
There's no way of factoring them any further. It's better to do them separate.
No. There's really, oh, I see what you mean. Well, you could write it like this. You could write this like this. You could write this as the integral. Let me rephrase it here. So this here, you could write that as pi times the integral from 0 to 1 of like y plus 2y to the half plus 1 minus y to the fourth minus 2y squared minus 1. And that would dy. You could, you could combine the integrals. You could. You could combine those integrals. Hold on here. And then, the 1 and the negative 1 would cancel. So that would save you a little work. But other than that, there's not much you can do. You have to just, and I just chose to get my antiderivatives separately for each one. Is that all right, Shalom?
Yeah, thank you.
Okay, good. Are there any other good questions? All right. Let me give you a moment here to copy down what you need to copy down. So of course we're putting in the limits. We're putting in the limits of 1 and 0. And when we put a 0 in those antiderivatives, we just we put in 1 and 0. And when we put a 0 in the antiderivatives, you're just going to get a big old 0. So that's what I wrote here. And now you have something that you could type all this in WebAssign and it would mark it correct. WebAssign wants simplified radical answers, so it's going to want that pi there. Okay. Don't go, approximating pi or anything, on your homework or on your next exam, because it'll count it as wrong, because it would be wrong. Right? You wants the exact answer. Okay, and so we're going to have here, like for instance, 1 squared over 2 is a half. This here, 1 to the 3/2 is 1, so you have 4/3. 1 to the 5th power over 5 is 1/5. And 2/3 times 1 cubed is 2/3. Okay, and so if everybody's okay, I'll move to the next page. If everybody's good. Are there any questions? Okay, so here we are. And you could just, Yeah, I decided to get common denominators and just, work it out all by hand. But I know at this stage, like your TI-84, 83 calculator, you can add the fractions and then can use MathFrac to get like a simplified fraction. I'm sure Desmos has uh, nice things too for fractions. So, I mean, if you were to type, let me ask you, if you were to type a half plus a 4/3 plus 1 in Desmos, would it give you 17/6? Would it do that? I'm going to try that right now. Half plus 4/3 plus 1. I'm just kind of curious. Let's see, a half plus 4/3 plus 1. Whoops, hold on. Hold on. I know there are a few chats there. Hold on. A half plus 4/3. Man, I'm going to have to, hold on. Just give me a moment. 1/2 plus 4/3 plus 1. I'm saying a decimal. I'm not saying a fraction. Let me see. There were a few in Desmos. There were a few chats on that. Yeah. So, you're going to have to just, use your math skills, and you can do it. And you'll get 29 pi over 30. That'll be the answer for your volume. So the volume of this interesting solid, okay, which I mean, it's an interesting solid. It's going to be 29 pi over 30. And maybe we're talking, cubic inches, cubic centimeters, cubic feet, whatever. But that's the exact volume. And the exact volume is important because, like you might have noticed that a lot of these, if you go in the grocery store, some of these products, like snack pack puddings and so forth, the products have interesting shapes. And but you want to know what's the exact volume of pudding, say, in your container or Jello or whatever it is. Well, the exact volume is important because if you approximate, okay, it might not matter for one container of Jello, but if you're making a billion containers of Jello, being off, your volume being off even just a little bit, it can add up to some money. So exact volumes are always desirable. And as a matter of fact, this entire science in section 6.2 was developed because merchants wanted to be able to determine how much wine was in like wine barrels. And wine barrels have interesting shapes. The barrel, the way the wood is constructed. How many have seen a wine barrel before? Yeah, Jonathan has, and if you look at a wine barrel, it has an interesting shape, but it's not like a cylinder or a sphere, or so yeah, ovals with flat ends, right? That's right, like this. Okay, and I'm not an expert why they make the wine barrels that way, but there's a reason, I'm sure. And you want to find the volume of your wine. You want to have an exact volume. You don't want to be off. All right. Are there any questions on this? How many think this is kind of cool? What you're learning, finding these volumes. Okay. Jonathan's liking it. Susanna's liking it. Mark's liking it. Wonderful. Wonderful. Okay. Well, let me. If there are no questions, I'll stop the recording. Are there any questions before I stop the recording? Okay. Very good.